Welcome one, welcome all to a brand new unit in the world of energy and society. As usual, when we start off with any brand new unit, I always like to cover terminology first. All right, so you may have heard of the words work and energy before, and you may think that they're the same meaning, but they do have slightly different meanings. All right, first off, let's just talk about energy. All right, and energy in general can fall into two separate categories: either energy that is stored or energy that is currently in motion. And in elementary school, you may have heard of the fancy words for it. For example, energy that's stored is often coined as potential energy. All right. Energy, by definition, is the ability or capacity to perform work, by the way. And in the world of potential energy, it does fall into many small subcategories. The one that we'll be focusing on is gravitational potential energy, and that's the reason why it's been underlined. All right, so that's our primary focus, at least right now. There are other forms of potential energy that exist as well through your readings in the textbook. All right. Last night I did ask for you guys to please read ahead for the next chapter, so pages 222 through 235, and it briefly mentions all these terms here. Okay, so for grade 11, we're going to focus on gravitational energy at the first part. We will deal with nuclear energy, which I guess is not really mentioned here specifically, but I suppose it'll fall into the world of radiant energy. All right. So those are the two primary ones we'll be talking about in this unit. And we'll also be defining kinetic energy as well. All right. Now, many of us may think that kinetic energy has to do with an object that's physically moving, and that's true. That is one version of kinetic energy. All right. But there's also another one that exists as well, and this is the weird one. Temperature is also classified as kinetic energy. So right now we're only going to be focusing on mechanical kinetic energy, but eventually we'll be talking about thermal energy by next week. All right. So in today's lesson, we're just going to be strictly focusing on mechanical energy. So gravitational potential energy, which is mechanical energy, as well as kinetic energy. So the energy stored in physical objects, that's our primary focus right now. So I've already given you the definition of energy. Well, here's the definition of work. Work is the transfer of energy. So it does seem rather cyclical here, right? Energy is the ability to do work, and work is the transfer of energy. And it seems to just be going around in circles and circles and circles, all right? And I think it's helpful to know that, yes, there is a formula to describe energy and work, where by definition, work is equal to delta E. And remember, delta means change in. So work is equal to the energy you have at the end, subtract the energy that you have at the beginning. All right. So initially you may have stored energy, and when that stored energy goes into action, now you're performing work. Energy is measured in SI units of joules. All right. So that's the unit that we'll be using here. Joules is named in honor of James Prescott Joule. He was a thermal engineer, and he was able to prove that the energy that exists in temperature is the same energy that exists in moving objects. Okay, and we'll share that next week as well. So in honor of him, the standard unit for energy is measured in joules. Now, if you're an American, for example, Americans, they measure distances in feet, yards, and miles. And here in Canada, we measure distances in meters, centimeters, and kilometers. All right, so we have an SI unit notation for distances. Joules is the SI notation for work and energy. If you're an American, you won't measure it in joules. Instead, you'll measure it in calories. All right, so calories is a measurement of energy. It's just for a different unit of measure, and there is a conversion ratio. We'll cover that later on as well. All right, is that enough time for everyone? If anyone needs additional time, just please raise your hand. Okay, so when you guys drop your hands, for those that have raised your hands, then I'll move on to the next slide. I think things just to add during this downtime, again, guys, once you're done jotting it down, just remove your raised hand so I know to advance on. What story do I want to share with you guys? Oh, yeah. This unit over here, if you look in the timeline, we were fast forwarding over 100 years into the future. All right. So this is well and beyond Newton's time. So again, Newton, he existed in the 17th to 18th century, and this is early 19th century technology over here. with regards to joules. All right, so Isaac Newton, he had no notion of what energy was. He knew that things stored something, and it was stored when the object was in motion. All right, so objects that are in motion, he coined it as momentum. So you may have heard of that term before. Momentum and energy are not the same thing. All right, they seem like the same thing, but they're not. Momentum is a quantity that exists with an object in motion, and it's classified as a vector quantity. More of that in grade 12. So in grade 11, we're skipping out on the last half of Isaac Newton's research into, objects as they collide with each other. And we're just fast forwarding about 100 years into the future. And we're just talking about what is stored in objects, all right, which is energy. Okay, so yeah, we are fast forwarding a bit in time. All right, that buys me enough time to move on to the next slide. Again, we're just strictly focusing on mechanical work for today. And then next week, we'll move on to thermal energy and then nuclear energy. So there are 3 parts to this entire unit. By definition, if you're talking about mechanical work, that's the energy that's used up when you're physically moving an object. All right, so a force has to be applied and the object has to physically move in the same direction as the force applied. That's the definition of work. Okay, force times distance. So at the end, yeah, you'll see a formula that looks like this. Work is equal to force times distance. But I always like to talk about the story behind how the formula comes to be. All right, that way you can better appreciate what it is as opposed to just memorizing a formula and not really knowing about the backstory behind it. With regards to plotting out graphs, graphs are always labeled by the dependent value versus the independent value. All right, so if you're in math, you'll call it, the y versus the x. So that's why force will be on the y-axis and distance will be on the x-axis. Of course, in physics, we don't call it y and x. All right, we call it dependent and independent. Okay, those are the proper terms for it. So that's what we're creating right now. We're creating a special type of graph called a force versus distance graph. And if you're wondering why are we drawing this, well, let me just give you an example of me trying to move this box, for example, right? So this box is moving on top of a platform. So I'm pushing it with an applied force and it remains constant, all right? And as you may know, as I'm pushing it through a distance, the graph would start looking like what you're seeing in the animation right now. The further I push it, the more distance I travel, and you'll see that I'm forming a rectangle and the area of the rectangle gets bigger. Now, let's say that I want to upgrade this experiment. So not only is it a box, but I'm going to throw a calculator on top. With the additional calculator on top, you'll notice that I'll have to apply a greater force when pushing this. All right, so now I'm applying a greater force over the distance. And yet again, I'm producing a rectangle. And since I'm creating a rectangle, that surface area of the rectangle can be measured. In fact, the surface area of a force distance graph, by definition, is what work is. All right, so the work, by definition, is the area underneath a force distance graph. If the shape of it looks like a rectangle, the formula is fairly easy, right? Because we know that rectangles are base times height, and that's all we're doing. All right, so base times height ends up with that formula there, or in this case over here, height times base. So that's the origins of this formula over here. All right. In other words, if you have the force times graph and it doesn't look like a rectangle anymore, but instead looks like a triangle, you'll probably see a 1/2 in the formula. And springs, they do behave weirdly like that. You'll notice that with elastic bands and springs, as you stretch it, the force that you apply will gradually increase. So the graph would not look like a rectangle anymore. When you look at the formula, you'll see that there are no arrows on top of the variables. Work is a scalar quantity. In fact, this entire unit is a scalar unit. All right, so maybe that's benefit for some of you guys that are fearful about vectors. Now, I'll briefly talk about vectors here and there because we got to deal with the component that allows us to do work. But other than that, we're not multiplying one dimension into another dimension or dealing with multiple dimensions at once. Okay. So work is a scalar quantity. There is no, work forwards. There's no work backwards. The common joke that I usually say to students is that, let's say that I'm walking across this way. As I walk across this way, I'm burning 1 calorie eventually. Does that necessarily mean that when I start walking backwards, that because of the vector, I start to get fatter and fatter and fatter? And that doesn't work, right? You can't just start walking backwards and start to gain calories. You're going to burn calories no matter what, as long as you walk, right? So it's another reminder that work is a scalar quantity. For your references, in case if you want to write that down, work is measured in joules, force is measured in newtons, and distance is always measured in meters. Okay, now that we have our official formula, there are small little catches to this formula here, all right? Because there are cases when work is not accomplished. If you look at the formula, in order for you to have a numerical value for work, that means that either of these two values over here cannot be 0, all right? So for example, let's say that I decide to press against this wall, okay? I push as hard as I can with all my might. If the wall does not budge, am I doing work? And if you look at the math, because I'm not moving, then by definition, work is not accomplished. Okay, so if there's no distance traveled, I'm not doing any work. Here's another weird example. Okay, I decide to put on, a 50-pound backpack behind me. All right, and then someone gives me a push initially. They're probably doing work as they're pushing me. All right, but then I start moving at 1 meter per second towards the camera. And as I'm moving at 1 meter per second towards the camera, am I doing any work? In fact, the camera can be 100 meters away. All right, and I'm just walking towards the camera. Am I doing any work during that 100-meter walk? I am sweating. All right, I am tearing up. I am in pain, but that has to do with the inefficiencies of my body. If my body was more efficient, let's say I replaced my feet with wheels, you'll know that naturally I'll just roll towards the camera. All right, so work is not accomplished if I'm not applying any sort of force. So inertia doesn't count, all right? And again, inertia is just a natural characteristic of anything that has mass. The greater the mass that it has, the more inertia it has. So the person who accelerated me at the beginning, yeah, they were doing work. But me just naturally gliding towards you guys or towards the camera in a straight line, I'm not doing any work. So those are the two consequences of work. Okay, or the two exceptions of work. If I'm not carrying any distance, I'm not doing any work at all. In other words, if your parents were punishing you because you weren't doing any homework and they found out about it, well, one classic punishment is that you take out a textbook, you put it on your hand, and you just stretch it out like this all afternoon for a good half an hour. All right. In this case over here, by the definitions of physics, you're not doing any work at all because the textbook's not moving. Does your arm hurt? Certainly does. Again, it has to do with the inefficiencies of our body. Okay, that's why when you go on a treadmill, you burn calories. You're not moving anywhere, but you're burning calories due to the inefficiencies of your body. As I said, if your feet were replaced with wheels and then you just slapped yourself on a treadmill, you'll notice easily right then you're not doing any work. I think there's a viewer question. No, there wasn't. Okay. Is that all I have to share with this slide here? Oh, first example. Okay, so example 1A. How much work is it to pull a heavy box at a constant force of 8 newtons forwards for a distance of 25 centimeters forwards? All right, some have gone through the calculations. That's awesome. Let's just go through the formalities of this. All right, so let's move on to the next slide. Anyone else still need the slide? Just a raise of hands before I move on. Okay. Yeah, just drop your hand once you're ready to go so I know how to advance at that moment. While you guys are working away at this, remember that you need to stick with the MKS units. That's a memory aid, okay? MKS. All right. In fact, during this pause over here, I need to explain this at some point in this course. This whole word called fundamental units. Meters, kilograms, and seconds, they all fall into that category. These are fun and exciting units. They are the fundamental units. What does it mean? In simplest terms, fundamental units are units that cannot be broken down any further. In other words, they cannot be represented any other way. All right. Because when I say when it can't be broken down any further, there's always going to be a student saying, hey, sir, can't you break down meters into millimeters? That's not what I'm talking about. I'm talking about breaking down meters into another unit to describe meters, and that doesn't exist. All right. There's no smaller unit to describe a meter. right? And that's why meters, kilograms, and seconds are fundamental units. In fact, in high school physics, we cover 5 fundamental units. So we got our distance, our mass, our time, temperature, and funny enough, temperature is not measured in degrees Celsius. It's measured using capital K, okay, measured in Kelvin. And the last one is current, measured in amperes. All right, so at some point you're going to see that I'm going to use these fundamental units or incorporate them into a bigger problem. Okay, so fundamental units are units that cannot be broken down any further and represented by other units. However, there are units that exist in physics that are not fundamental units, and they're called derived units. Maybe I'll just write it up here. All right. And we've covered a few derived units already. For example, the last unit, we covered the Newton. All right. A Newton is not a fundamental unit because a Newton can be described by a kilogram times a meter per second squared. The same is also true with work and energy measured in joules. It too is not a fundamental unit. It can be measured in newtons per meter, or it could be broken down even further, right? Shall I cover it here? Yeah, why not? Let's just cover it right over here, okay? Again, we know that 1 Newton is equal to a kilogram times a meter per second squared. So by definition, a joule is equal to a kilogram times a meter per second squared times yet another meter. So 1 joule technically is equal to a kilogram times a meter squared over a second squared. So the joule is the derived unit, and kilograms, meters, and seconds squared, these are all the fun and exciting fundamental units. Okay, so yeah, I'm just trying to burn some time right now. I think everyone is all done, and now you're aware of this stuff over here. And if you're curious, do I need to copy this down? I will be explaining this stuff multiple times. All right, so if you want to jot it down the first time here, you can.
Could you put it back on the board?
It's still up on the board.
You're erasing it.
I'm just erasing down all the scribbles. I can leave this one over here, though. Okay, all I'm doing is I'm breaking down a joule into its fundamental units, knowing that a Newton is equal to a kilogram times a meter per second squared that we covered from class.
So what does denied mean?
What is what?
Denied.
Derived. D-E-R-I-V-E-D. When you derive something, that means that this came from something that was bigger or something that you knew from beforehand. Okay, like deriving equations. You're making something new from something you knew in the past. All right, so you have your fundamental units, which is all the base units, and then you're making something new from the fundamental units, and that's why it's called a derived unit. Raise of hands, anyone else still need a bit more time for this? Okay. So again, I think if there's anything to jot down that's more relevant, it would probably be what you're seeing on the far right-hand side right now. Because I'm going to be talking about this concept yet again, probably towards the end of today as well. Okay, fundamental units and derived units. All right, so I'm going to take example 1A. I'm going to bring it all the way to the top. Okay, or all the way up here. So it's the same exact question here. I also kept mechanical work. That was from the previous PowerPoint slide as well. Just to remind you that by definition, work exists when you apply a force and you travel a distance in the same direction. So we look at this example over here, and luckily we have forwards and forwards. All right, so now we're doing work, or at least positive work. Now, that previous thing about fundamental and derived units, again, we're sticking with the MKS system. So we don't measure our distances in centimeters in physics. Instead, we measure it in meters. Okay, so in our givens, our force applied, yes, it's 8 newtons. We're going to assume that that's the positive direction of travel. And we're moving in the positive direction of travel of 25 centimeters, which translates into 0.25 meters. All right, so we have our givens. Our required would be work. How much work are we performing? Work by definition is force applied times distance. So 8 newtons times 0.25 meters. And yes, we do end up with the answer of 2 joules. the student asked or stated earlier. All right, it is 2 joules. And if you want to get technical with it, 2 sig fig problem plus or multiplied by another 2 sig fig problem, our answer will also be 2 significant figures. So technically, it should be at 2.0 joules. And just as a reminder, it doesn't even matter which way you're moving. In this case over here, I could be pulling the box backwards. But as I'm moving the box, pulling the box backwards, it too is also moving backwards. So work is always accomplished when the object moves in the same direction that you're applying the force. That's when positive work is done. Here's a similar question. Okay, how much work is it to pull the same exact box, but this time around, you're pulling at 8 newtons at an angle slightly upwards? I think I have a picture over here, just so you have a better appreciation of what's going on. So this time around, you're not just dragging the box across. Now you're tugging it at an angle. One thing that's not mentioned here is the mass of the box. So let me just tell you this. Assume that the box is heavy enough that it doesn't fly off into the air. All right. In other words, you're dragging it at an angle, and the box just physically glides like so. Is that animated out? No, I did not animate it out. Okay, so you can imagine that the box is just being dragged across like this. So before you get to your answer, here's what I want you to think about. Okay, as you're dragging it at a diagonal, all right, is the box moving up or down at all? Right, it's not. So in other words, any effort that you put in the vertical dimension, you're wasting that effort because it's not moving. It's almost as if I'm trying to pick up this box vertically and it's too heavy for me to lift up. I'm not doing any form of work in that dimension, all right? The only useful dimension here is the fact that it's being dragged across. So that's why we have to pull back a little bit of trig in solving this again, all right? And this is the only aspect of vectors that we need to deal with. We only care about that portion of our force that allows us to move the box. Some of you guys already know the answer and you've typed it out there. That's perfect. Yes, students, do you have a question?
Yeah, I was wondering if like for questions like these, we should draw an FBD.
Okay, good question. In general, yes, you should draw a free body diagram. All right. But when it comes to test time, normally I'm giving you questions that are so straightforward, you'll probably know the answer without having to draw it out.
Okay, thank you.
Yeah, no problem. All right. Because we're only briefly talking about forces, I think only on 4.01. We don't talk about forces anymore beyond there. Okay, so yeah, in tonight's homework, you'll see free body diagrams, but beyond here, you're not going to see any more free body diagrams. They're helpful in explaining how to solve problems. And yes, for sure, apply it in the first night's homework, but beyond here, you're not going to see the word force anymore. Okay. All right, so let's continue with our logic over here. We know that only this red vector here helps us in moving the box. If we do draw a vertical vector, well, that, as I said, that effort in lifting it vertically is wasted away. So when we take a look at this side over here, because it's beside our angle that we described, we're going to multiply it by, remember, the hypotenuse. All right. So the red value of your value of f, I guess you want to call it f of x, that is equal to the hypotenuse times the cosine of that theta that's been given to you. Okay. My point there is that the formula work is equal to force times distance. That's the easiest version of the formula, but you'll notice in your textbook, they give you a slightly longer version of it. In your textbook, it will look like this. And I hope that you have a better appreciation of why they decided to throw this value in there. Okay, why did they put in cosine of theta? It's just so that they can guarantee that you're talking about the work in allowing the object to physically move on that surface top. Okay, that's why they included cosine of theta. I normally don't write it out this way because I find it takes way too long to write it out because of the brackets. So my normal way of notating it is work is equal to force applied, sure, times distance, and I'll multiply by the cosine of theta afterwards. Because anytime you write it out the notation this way, you don't need to include the brackets, all right? There is no confusion here. We needed the brackets because if you wrote down 15 degrees and then you had a distance of 3 meters, well, what are you going to do with cosine? Are you actually going to do cosine of 15 degrees times 3 meters? No, you're not going to do that, right? You're doing the cosine of 15 multiplied by force applied and then multiplied by the distance. And that's why you need to have the brackets, at least in the way how the textbook writes it. Okay. Meanwhile, if you write it out using my notation, you won't need brackets at all, and there's no ambiguity in that statement. So when it comes to test time, it's up to you how you decide to write it out. You can either use the textbook's format or you can use my format. They're both fair. So when calculating, we only focus on the horizontal and not the vertical. We only focus on the one that allows the object to move. All right. In these questions, normally the angle is always measured relative to the horizontal. That's why we use cosine of theta. As mentioned, your vertical force or your vertical effort, it's wasted away when you don't move the box. You're not doing any useful work vertically, right? Your only useful work is what is allowing the box to move horizontally. Okay, so now we can sub in our values. Okay, 8 newtons times the cosine of 60 degrees. 8 newtons times cosine of 60 degrees works out to just 4 newtons. So of all the 8 newtons that you're pulling, only 4 newtons of it is actually useful in helping to drag the box. Right, so that 4 newtons, that horizontal component that allows you to drag the box, that you're dragging for half a meter. So 4 times half a meter gives you 1 joule of work. That's where that comes from. I'll erase my scribbles. Any other questions, guys, before we move on? Yes, student. You can type away or you can ask away. Thank you. Thank you for letting me know. And please let me know when you're ready to move on. Another one is, do we need to think about friction? It has mu k. Now, friction will slow down your efforts, right? So it's not going to help you in doing your work. So when you take a look at your net work or your total work, friction usually inhibits your useful work. And you'll see that in an example coming up in, I think, the next slide or the slide after. Okay, when 2 slides from now. Okay, so we will factor in friction in 2 slides. Okay, so far so good for now. Again, I just want to start off with the most straightforward examples and then slowly ramp up with this. Okay, again, work, you'll notice that there's no arrow on top because work is a scalar quantity. Okay, so this work that you're doing this in the setup over here, it doesn't matter if I'm dragging it, at that angle this way or towards you at that same exact setup. The work that I'm doing that's useful in moving the box is just 1 joule. That's it. Okay, it is a scalar quantity. Now, even though it's a scalar quantity, there is such thing as negative work. All right, and that's what the next slide is talking about. Even though work is a scalar quantity, there is a difference between positive work and negative work. The best way for me to give you that example is with regards to me lifting up my coffee mug. All right, as I'm moving this coffee mug up, you'll notice that I am burning some calories, and that's because I'm applying a force upwards. It's fighting against gravity, right? So I'm applying force upwards, and it's moving a distance. So whenever I'm lifting this bottle up, I am performing positive work because the bottle is moving in the same direction that I'm pushing it. Okay, so positive work is accomplished when you apply force on the object and the object moves in the same direction that you apply it. On the other hand, you'll notice that, again, because of the inefficiencies of my body, I'm going to get tired and I'm going to have to let this thing come down now because I'm just getting tired with it. Funny enough, as I let this come downwards, now I'm doing negative work. And the reason why I'm doing negative work is that even though I'm trying to apply a force upwards, well, unfortunately, I'm losing right now, and that's why it's going down. All right, I didn't let go of it. I just can't sustain it anymore. So even though I'm applying a force upwards, unfortunately, I'm losing and the object's moving down. And this is a case where I'm doing negative work. The interesting thing about negative work is that the consequence of it is that now this object is doing work on me. You can imagine if I had a teeter-totter right now, maybe I'll just draw a picture on the screen. Okay, what's going on? If I had a teeter-totter lying around, and here is my coffee mug, and then here's a lovely parcel. Okay. If I can't hold on to it anymore, oh no, I can't hold on to it anymore, and I let go of it, and I let the mug drop, well, now that mug is converting that stored potential energy into kinetic energy, and you can imagine the outcome that it will result in afterwards. Okay, if I drop the mug on a teeter-totter, that parcel on the far end, if it's light enough, it's going to get launched up into the air. So so there's stored energy there, and it is doing work. All right, as it's coming downwards, it's doing work. It's just that as it's going this way on me, unfortunately, I can't store that energy. Right? If I was more useful, like a elastic band or a trampoline, then yeah, I could store that energy and release that energy afterwards. But the inefficiencies of being a human being, yes, I'm going to probably lose more calories while I'm dropping down here. So even though it's doing positive work on me, which is technically correct, I'm doing negative work. Okay, I am doing negative work. Okay, so that's the difference between positive work and negative work. And friction, unfortunately, always performs negative work. Some people have calculated out already. That's awesome. All right, so now let's deal with the total work with friction involved. I could include a mu k. In fact, I think in your homework, there will be examples where there's mu k in there so that you can sit down and crunch through it. And I see a lot of people are jumping to the answer, and that's perfectly fine. Remember, as a reminder, guys, with regards to your j, it should be a capital J. Okay, when you use a lowercase j, especially if you go into electrical engineering, let's say, that means that now you have a complex number. You have an imaginary number. So 1.5 lowercase j means the imaginary number 1.5. Okay, there is a lot of grammar in science. Physics, it's fairly strict. All right, it's pretty much as strict as computer programming. I don't know if you guys have programmed before, but just accidentally using a capital case or a lowercase or adding too many spaces, that can actually ruin program code. All right, and with regards to physics, when you write things down, I know that we're human beings and you can probably interpret what's going on. For example, if I said that I was pushing a heavy box at 8 newtons, you probably would know that I'm talking about 8 newtons over here, but grammatically it's incorrect. All right.
Computer programming is really strict.
Yes, programming languages are very strict. All right. And it's just the reality that computers, they're not intelligent. They're really good at doing things very quickly, but they're not intelligent at correcting things. I know there's AI technology now, and that's compensating for it.
I think it's probably better than worse that they are not intelligent, because then they could become omnipotent.
Oh, they're getting there. They are getting there.
They will.
I will talk about that later on in further discussion. But remember, student, right now, this is a video recording. It's going to be posted. All right. So I just want to stick with just the content right now. We can discuss all the small things afterwards. Okay. So let's just focus on this example right over here. There's a box. We're pulling it or pushing it 8 newtons forwards. However, there's friction as well in our problem. So the question is, what is our total work? You can think about it as your total useful work. All right. In your mind, if you want to think about it that way. So the total work is equal to the work applied plus this work of friction. And the sad part is that friction always produces negative work, and you'll see it as a consequence in our calculations. Okay. All right. So the work that we're applying is equal to force times distance. So 8 newtons times 0.25. Yes, that will give us the 2 joules that we had before. All right. So we had our 2 joules that we did have before. Unfortunately, with friction, remember that friction applies a force in the opposite direction. That's why the force of friction is at negative 2 newtons, because it's opposing the direction of travel. As a consequence, when it's going against our direction of travel, that results in a quantity that is negative. So 2 times a quarter gives you negative 0.5 joules. So 2 joules plus negative 0.5 joules will consequentially drop our final value down to 1.5 joules at the end. So yes, those that have answered earlier, you are correct. It's 1.5 capital J for joules. And another nitpicky grammatical thing, and you've seen that I followed through with this, is that grammatically speaking, you always put a space between the measurement and its unit. It's just part of the grammar. Okay, and that's the reality of friction. Normally friction is just converted into heat. All right, so you can imagine that happening, right? As I'm dragging this across, the two surfaces are rubbing against each other, and it is getting hotter between those two surfaces. Okay, why does it get hotter between those two surfaces? We will talk about that in our next section of this unit. Okay, so next week we'll talk about the consequences of friction and why friction generates heat. There's another way of approaching this question here. All right, is this it for today's lesson? We're getting close to the end, I think. Oh, no, we have to derive the formulas. Okay, so this is something just to think about on the side. You don't have to do the calculations to the right of this, but it's just a way just to show you that units, calculations, they always work out. Okay. Another way of interpreting this friction over here is effectively, again, work is equal to force times distance times the cosine of theta. All right, so if I'm physically trying to move the box this way, okay, I'll say that this is the positive direction of travel. Well, we know that friction is 180 degrees in the opposite direction. So effectively, with friction, you're calculating out 2 newtons times the cosine of 180 times that 0.25 meters. Before we get there, guys, I want you to try calculating it out. What does the cosine of 180 always give you? Exactly, -1. All right, cosine 180 always gives you -1. And I hope that logic makes sense. Friction will always generate negative work. So when you travel 180 degrees or you go in the complete opposite direction, you end up having a quantity that will have a negative measurement at the end. Okay, so again, the stuff on the right, do you need to do it that way on a test? No, you don't. But I just wanted to prove to you that, yeah, the calculations always work out. It's one of the beauties of, you know, how math and physics jive together. And a student asked, couldn't we just do 8 newtons subtract 2 newtons times 0.25 meters? In fact, that's what we did earlier, right? Don't forget to multiply the 8 newtons by 0.25. Oh, you factored it out. Yes, it will give you the same answer that way, and you'll see kind of why that works out at the end. All right, because as I said, effectively, what you're effectively doing over here is that your total work is, technically speaking, your net work. All right, your net quantity. So if you treat it the way how you're solving it, where you're treating it as work net is equal to force net times distance, you'll see that's why the math works out. Okay, student? So you could do that, and logically it is correct. It's just that, you know, then you're missing out on that grammatical portion of it, because we don't call it net work. We actually just call it total work. Okay, so that's the first part of today's lesson. Okay, work is equal to force times distance. But now we want to create equations to describe, well, how much energy exists when I lift this bottle all the way up here. Okay, because we know there's stored energy in there. So what is that quantity? And to figure out that energy, yes, the potential energy. And to figure out that quantity of potential energy, it all stems from the definition of what work is, right? Work by definition is force times distance. All right, so the amount of work that's required for me towards lifting up this bottle over here is equal to the force that I'm fighting against, which is the force of gravity of this bottle itself, times the distance that I'm physically moving it up, right? And we know that the force of gravity acting on this object over here is equal to mg. That's what we learned in the last unit. Fg is equal to mg. In other words, the work that's required in me lifting this object up is equal to m times g times the distance. And since this is a vertical distance, often out of simplification, we don't call it delta dy, we just call it delta h for a change in height. Okay, because I started off somewhere over here, and eventually I'm up here. So there's a difference in height. Okay, so now we can figure out how much work it takes into lifting an object. It's equal to the mass of the object times the gravitational field strength of the planet you're in and the height you physically move it up. So yeah, if you're on the moon and you're lifting up the same exact object, you're doing about 6 times less work. And that's because the value of g on the moon is 6 times less than that on Earth. All right, and the same or something very similar is true when you're on Mars. The gravitational field strength on Mars is, it's not exactly 3 times, but just for, you know, quick mental math, it's about 1/3 of that of the Earth. All right, so yeah, you're doing almost 3 times less effort in carrying things when you're on Mars. And that's one of the challenges that, for example, astronauts have to deal with when they're in deep space. right? Or sorry, if even if they're in the International Space Station, right? Because they don't have to worry about, you know, the gravitational forces there as they're experiencing microgravity. Their muscles aren't getting any work. And that's why you'll notice that as daily exercises, they have bungee cords strapped onto them while they're running on a treadmill. That way they can give their muscles the minimum amount of exercise they need daily so that their muscles don't just eat away at themselves. Okay. Your body typically, when it's trying to look for energy, it's fairly lazy. All right. It wants to find energy from the most easiest source in your body. So no, it's not going to go and try to digest your food first, because that takes a lot of effort to digest your food. Instead, it's going to steal the energy from something that can take proteins from, like from your muscles. All right. That's what happens when you don't exercise for a long period of time. Your muscles degrade because your body needs energy, and it takes the easy way out. You'll take it from your muscles first. Okay, so let's go back to this stuff over here. Okay, so yeah, this is true. This formula is correct. Work is equal to mg times delta H. That's 100% correct. But if we want to find out how much potential energy there is in here, well, then I need to change this formula by a bit, because we know that work by definition is equal to the change in energy. All right. So in other words, I'm usually starting off with this. I know you can't see on camera, but I'm starting off with it on its lowest height. Let's say that the tabletop is the lowest height, and then I physically lift it up. So effectively, I'm doing work is equal to EF minus EI. But initially, because it's sitting on the table, EI is equal to 0. What I'm trying to get at is that if this cup or this mug is just standing over here, and then I lift it up a particular distance, well, now this object here will store the same amount of energy as my work. That's what I want to get at, okay? The work will be equal to the same amount of energy that was put into in lifting it up. And that's how we're able to derive out the official formula. Okay, so in your textbook, EP is equal to mg delta H. Some textbooks will call it PE, as in phys ed, is equal to mg delta H. Those are the American books. Let's just stick with this notation here, okay, EP. P is for potential, because remember, now we're storing it as potential energy. More specifically, gravitational potential energy. So yeah, there are some textbooks that will call it EG, all right, for energy of gravitational potential energy is equal to mg delta H. Okay, that I've seen that variant as well. We'll stick with this one.
Quick question.
Sorry, yes, please ask.
If it's EP times mg delta H, shouldn't it be delta EP?
Sorry, delta what?
Shouldn't it be delta EP this times delta H?
Okay. I don't want to get to that level of technicality, because when you get to delta EP, that means that now you're changing your energy. Now you're doing work.
Yeah.
Right. We're talking about the energy that's stored. We're talking about it as a state, all right, as opposed to a path. If you've heard, we're talking about the state that's in it. Okay, so it's the amount of energy that's stored when it's physically up here.
Shouldn't we just write H and no delta H?
Again, I don't want to get into all the semantics, and the reason for that is because this is the introduction to this world, right? As you continue in your studies in science, you'll hear all these weird little exceptions, all right? And I'll save those little exceptions for the future grades. Okay, so for now, guys, we're just going to follow the basics right now. I will show you, I think, probably later on this afternoon, the proper way of stating these things, just to let you know there is a proper way of stating it. But let's just start off from a grade 11 perspective first, and then, you know, we'll get through all the technicality things afterwards. Okay, is this equation our equation on our equation shape? Yeah, EP is equal to mg delta H. All right, we'll just have the delta here. We'll use it here. Okay, so yeah, that's the formula on your reference sheet. EP is equal to mg delta H. Some textbooks will use EG, and that's fine as well. Yeah, it has the same meaning. Okay, you could also write it as EG is equal to mg delta H. Just depends upon which textbook you're going from. That's all. And to me, when it comes to test time, do I care which one you use? No, it doesn't matter. Use either letter. They're both fine. What you probably shouldn't be using is this one over here. All right, so don't use work is equal to mg delta H. That was just the story of how we ended up finding this formula, right? I had to do some form of work to lift it from here all the way up there, and now it's going to contain that energy. I mean, here's another way of thinking about it, okay? If this starts off from over here and I lift it up and I just burned 3 joules in lifting it up, we know logically up here it contains 3 joules of energy, okay? How could I have done, 3 joules of work and this only has 2 joules of energy? That doesn't make any sense, all right? I've now transferred my work from my body, my chemical energy, into mechanical energy, and now it's storing that much energy. So yes, EP and EG share the same meaning. Again, it just depends upon the textbook you're going from. Okay, EP and EG share the same meaning. It depends on which textbook you're going from. Doesn't matter to me which version you use. Okay, so let's go through this calculation. How much work is it to lift a 400-gram object up by 25 millimeters? And once we're done with it, how much energy is now contained in the object? When you're solving it, guys, be careful. Remember your memory aid, MKS. All right. Meters, kilograms, seconds. Remember, H is for height. We're lifting it up. We could also call it, for example, EG is equal to mg delta dy. Yeah, you could do that. Again, let's just stick with simpler notations. Okay, well, let's just keep it clean. All right, so this is an example where we start off with our givens. What do we know? Our value of G, we're assuming we're here on Earth. Don't forget to convert 400 grams into 0.4 kilograms. And 25 millimeters is also 0.025 meters. Make sure you show all your work, all right? Again, if you're trying to just figure out how much work was done over here, I guess you could use the W here. No, I don't want to go through that. I'll just call it EPH. I just want to cut to the chase. I don't want to get too technical here, okay? How much energy will it have? Well, let's just get to that. How much energy will it have? Well, the amount of energy that it has is equal to mg delta H. The mass of 0.400 kilograms times 9.81 newtons per kilogram times the height of 0.025 meters. Pull out our trusted calculator. 0.4 times 9.81 times 0.025. All right, I know that some textbooks will just use the number 9.8, and that's fine. The only reason why I'm using 9.81 is that at least I'm giving you 3 significant figures in your homework. One of the problems is that sometimes when you round to 2 sig fig, remember a 2 sig fig number has up to a 1% error. Sometimes when you're doing your homework, you might have forgotten to do a step, but that step only influenced your error. Sorry, 2 sig fig is up to a 10% error. Sorry. So when you show 2 sig fig, that's up to a 10% error, meaning that if you made a mistake in your calculations, any mistake that you made that's less than 10%, it'll give you the same answer, and you didn't know that you made a mistake. And that's happened many times in the past, all right, where students forgot to factor something in, and they thought they got their homework correct because it was rounded to 2 sig fig. Meanwhile, they did make a mistake. So that's why in the homework, I typically have 3 significant figures. That way, if you made a mistake, you can clearly see you made a mistake because your answer that on your calculator doesn't match up with the answer key. Okay. Again, when you show just 1 sig fig, you could be up to 100% off from your correct answer. When you show 2 sig fig, you could be up to 10% off. And when you show 3 sig fig, you could be up to 1% off. And that's why I like to show 3 sig fig. Would you accept the answer of whatever that you've listed down? Yeah, I would have been fine with it. Again, when you're solving these problems, every measurement has an uncertainty. Okay, every measurement has its own uncertainty. So in this case over here, just because this was 2 sig fig over here, that's why I had that measurement there of 0.1. Okay, so we know that this object now has 0.1 joules of stored energy, and the amount of work that was required in lifting it up was 0.1 joule. Make sure that when you type in your calculator, you're using the correct measurements. Mass is at 0.4 kilograms, and it's 25 millimeters, which is 0.025 meters. When you crunch it out, that's what you get on your calculator, 0.0981. So if you stated your answer as 0.0981 on a test, would I really care that much? No, I'd accept it. That's fine. All right. But in truth, as I mentioned many times before, every measurement has its own plus minus error. Okay. And to get to your correct answer in truth, you have to factor that in to know how many sig fig to state at the end. But out of simplicity's sake, for high school, normally what you do is you take a look at your givens, and if you see that your least certain measurements is 2 sig fig, your final answer is probably also going to be 2 sig fig as well. So I'll accept either. All right, glad I answered those questions. Okay. All right, so this has to do with regards to energy in lifting something up. Okay. So just so that you can have a better appreciation of what a joule is, best way of doing it is by just going and picking up a bottle of water. The plastic ones. I know they're not environmentally friendly, but just find one lying around. Okay. If you take that and you know that it has 500 grams or 500 milliliters of water, that's half a kilogram, right? So you take that half a kilogram of water, you multiply by 9.81, and then you lift it up by, I think, 20 centimeters. All right, just by about this distance here. Sorry, that will translate to 0.2 meters. Okay, so you take that bottle of water, you lift it up probably the size of your head. Okay, you just lift up just the size of your head, and that should work out to just 1 measly joule. There you go. Okay, that's 1 joule of work, lifting it up that high. Drop it down, -1 joule, turn back into your body. You just gain some weight. All right, so now you have a better appreciation of what 1 joule is. There, that's 1 joule. Lift it up again for another 20 centimeters. Okay, that's 2 joules. Okay, so a joule, it is a very small measurement. It is a very, very small measurement. If you want to relate this towards calories that you burn, if you guys ever gone on a treadmill before, you notice how much torture it is before you even hit the number 1, right? You turn on the machine, you walk away, sweat begins to start pouring down. You think you've ran a kilometer. Meanwhile, when you look at the calorimeter, I guess is what you call it, you'll see that you only hit 1 calorie. All right. And that's because the unit of calorie versus a joule, it's a huge difference. All right. In fact, it takes 4,200 joules to equal 1 nutritional calorie. Okay. So that's why this number over here is 1. But when you walk on your treadmill, well, you have to do this about 4,000 times before you burn 1 lonely calorie. That's the scale of order between the two. Okay, mechanical kinetic energy. Okay, so energy with an object in motion. Again, I want to go through the derivation again. When it comes to quiz, test, or exam time, no, you do not need to derive it for me. But I think that if you can see how the form is derived, you have a better appreciation of just how physics works. So let's go through that backstory. Okay, so to find out how much kinetic energy an object has, we go back to our fundamental formula. Work by definition is force applied times distance. We also learned last unit that F by definition is equal to mass times acceleration. So yeah, technically speaking, work is equal to MAD. All right, work is equal to mass times acceleration times the distance that you've traveled during your acceleration. So this is a correct formula. It will work. There's nothing wrong with this. The problem is that often when we see things that are already in motion, we never got to see what happened before my hand showed up on the screen, right? So we don't know what happened beforehand. In other words, we don't know the rate that accelerated, and we don't know the distance it had to accelerate. We just noticed that at the end of the day, now my calculator possesses kinetic energy. And that's all we know. All right. So while this is scrolling across, you'll notice that it's experiencing uniform motion. So it has a measurable velocity. So we got to take this formula over here and convert it into just a constant velocity. How do we do that? Well, for one thing, this A beside delta D, have we ever seen A in love with delta D before at the beginning of this course? Yeah, you probably have. If I pull out the kinematic formulas right on the right, you would have seen that there is one formula there that had A and delta D together with each other. So what we're going to do is we're going to take this kinematic equation over here, which I'll write using this version here. VF squared is equal to VI squared plus 2A delta D. I'm going to isolate for A delta D. So I'm going to bring the VI squared over. So I have VF squared minus VI squared is equal to 2A delta D. And then I'm going to divide both sides by 2. Therefore, we know that A delta D is equal to VF squared minus VI squared over 2. Another thing to keep in mind is that we're taking it that we're talking about the kinetic energy it has now that it's in motion. In other words, beforehand, the box was stationary. It wasn't moving, okay? So our VI is equal to 0. And then once it starts moving, it just maintains that uniform motion. It's traveling at a constant velocity. So your VF becomes your final V, all right? So your A delta D really is just your final value of V, whatever that you observe it already moving at, V squared over 2. Now we can sub this V squared over 2 into our A delta D. All right, so EK is equal to M times V squared over 2, and that's the official formula. Depending upon the textbook that you're getting this from, it'll either be written out like this, MV squared over 2, or it's written out this way, EK is equal to 1/2 MV squared. For all tests, quizzes, and exams, when I give you a reference sheet, it'll be stated using the second method. Okay, and here it is all PowerPoint animated out. It's the same idea. There you have it. And if you want to write it down, because you were previously taught that EK is equal to MV squared over 2, I'm fine with that. All right, it's just or preference. I prefer writing out this way because when you write it out in your homework, you'll notice that you only need to use one line of your line paper to answer your question, as opposed to using up twice as many vertical line spaces. All right, so it's just more space efficient when you write it out that way, and that's why I prefer doing that.
Are we allowed to just turn, like every time that we see the starting equation, can we just rewrite it as this? Say that it was rearranged?
You can, if you are able to rearrange it in your head, by all means, rearrange in your head. So in other words, if you know how to isolate for M already, then by all means, rearrange for M in your head. 2EK over M over V squared. Okay, so if you're able to rearrange in your head, that's fine with me. Otherwise, if you need to show how you rearranged it, that's fine. Just as a reminder, everything that I've written up here, this is just the story of how the formula was created. That's it. On a test, you'll just be starting off with this formula here.
Oh, okay. So that other stuff we don't have to know.
You can't get there.
Remember how I mentioned that, again, I want you guys to appreciate how formulas are created.
Yeah.
So, I mean, again, in today's lesson, I could have just said, okay, guys, here's a formula, mechanic energy. Just memorize it as EK is equal to 1/2 MV squared, and go and do some calculations with it. I have a feeling that some people over here probably learned it that way, and they just know that just to be a robot, just put numbers in here and hope for the best. All right. Yeah, you could do that. But then afterwards, when you're done with writing the test, you had no idea what you just did. You were just trying to get an A and move on. All right. Again, there is science behind the science, and that's why I'm going through this. All right. This is the story of how this science came to be. This formula isn't just randomly made up. There is logic behind it. Okay. And yes, there are some students that are grateful that I go through this effort. Okay. In fact, it's better off that I do it now. Why? Because this is the easy stuff in physics. All right. It'll get to a branch in physics where it's so mad complicated. You still want to know how the formula is derived, but it's just above and beyond your brain that sometimes you just accept the formula and you just go with it. All right. And it will get to that point, unfortunately. But right now, while we're dealing with what's this called? Newtonian physics. Yeah, classical physics or Newtonian physics. Pretty much every formula can be proven, all right, from a high school understanding. Okay, so let's answer example number 3 now. Okay, a 100-gram ball is moving at 50 centimeters per second. How much kinetic energy does this ball possess? All right, again, you didn't get to see the ball beforehand. All you see is that in front of your view, when you open your eyes, it's moving at 50 centimeters per second. All right, so go ahead, crunch away at it. Feel free to share that song with everyone at the break. All right. So we have another 7 more minutes or 8 more minutes to go. No, it ends at 10:15. Sorry. All right. So I'm going to be able to finish my lesson in the next 5 minutes anyways. Okay. All right. So now let's start solving this problem. Again, guys, remember MKS. All right. Meters, kilograms, seconds. Some of you guys have gotten to the final answer already. That's awesome. Again, make sure you show all your work. All right. How do you get to there? Again, start off with your givens. What do you know? You have a mass of 0.100 kilograms, just to retain the certainty. Your speed is at 0.50 meters per second. All right. Again, keep in kilograms, meters, and seconds. Okay, with those two as your givens, now you can solve for your EK. Where your EK is equal to 1/2 I'll write that at first, mb squared, which is equal to 1/2 0.100 kilograms times 0.50 meters per second, close brackets squared. In fact, after solving this, you'll get to see how the fundamental units come into play. All right, you end up initially getting 0.0125 kilograms times meters squared over second squared. And as I mentioned from 2 slides ago, instead of writing down this over and over and over again, because it's just so messy, why not just write it down as a derived unit? So that's why scientists will replace that mess with just a nice clean letter of capital J. 0.01, I guess 2 would be the correct answer. No, is it 3 sig fig this problem? 3 sig fig, 0.10125. Okay, that's how it came to be. Any other questions before we move on to example number 4? Okay, example number 4. 1 second. Okay, let me rewind back. Tell me when you're ready. Oh, other questions. Why are kilograms, meters, seconds the fundamental units? All right. Where did that whole story come from? It will take me a while to explain it all. Again, on my YouTube channel, if you go to it, you'll see a story called Fundamental Units. All right. And with that, it's about a 1-hour video to watch all of them. Again, we want to make an international standard. That was the whole purpose of this course here, right? I start off with the first day of, hey, I have this stuffed animal over here. I'm going to drop it. Now everyone time it. And when you saw in the comment section, everyone had a different time. And that's just the reality of doing experiments as a human being, right? We're all going to get slightly different measurements. But we saw the same exact experiment. Shouldn't we all have the same international answer? And that's why we ended up creating these units, right? Because, back in the good old days, they used to measure lengths using a person's foot, like a king's foot. But the moment that the king passes away, well, then you've lost that definition, right? And that's why we want to create these standards that even if you lose the original item, it's okay. You can reinvent that length again. So in physics, we just stick with these standards, okay? We stick with distances measured in meters, and that's all reference to light because light travels at a constant rate. We measure time in seconds, and that can be determined using a cesium atom, isotope number 133. That's why we call it cesium-133. And the last thing is mass measured in kilograms. Originally measured with water, from a 10 centimeter by 10 centimeter by 10 centimeter cube. But unfortunately, with the different isotopes of water, you're going to have a different definition every time. Okay, so we're constantly trying to perfect it so that we have a verbal definition of what this measurement is. That way, if you destroy the original one, you can recreate again. That way, the entire world, we're all following the same page and we're all getting the same answer. Okay, so that's why kilograms, meters, and seconds are fundamental units. It's because these are the base units where everything else is made from it afterwards. We had to start from somewhere. And funny enough, here's a weird part, okay? With batteries, you know that batteries are measured in volts. But as I said, M kilograms, seconds, current, and Kelvin, that's our fundamental units. So where did volts come from? As crazy as it sounds, a volt can be defined by these 5 variables as well. Same as resistance in ohms, okay? So these are the basic building blocks to create everything else that's beautiful. I know I'm running out of time, so I got to cut to the chase. All right, well, let's get to our next example. Okay, so how much work is done by accelerating a 1 kilogram ball from 4 meters per second to 8 meters per second? Okay, I think some people accidentally will get to their answer of 0.5 times 16. So some people will end up getting the answer of 8 by accident. And just to let you know, 8 joules is not the correct answer. Delta E means change in energy, which is definition of work. Okay, so no, it is not 8 joules. I think a lot of people, as I said, they're tempted just to do 4 meters per second, subtract 8 meters per second, which gives you 4 meters per second. You got your 1 kilogram for your mass, and then they subbed it into this formula here, but it will not work out. You're going to get to the wrong answer. All right. In fact, it takes more effort to go from 4 meters per second to 8 meters per second than it did to go from 0 to 4. All right. I mean, if you tried, speeding up a car, it's very easy for it to speed up at the beginning, but afterwards it gets tougher and tougher and tougher. Right. You'll see your car struggles as it's on the highway just to go up by an additional 20 kilometers, as opposed to when you started from rest. It was very easy. Okay, so with these questions over here, I'll give you a graphical representation of why this is wrong and why it's true. But let's just solve this using math first. Okay, this is asking how much work is done moving from 4 meters per second to 8 meters per second. In other words, you're already in motion. All right, you didn't have to put in any work from the 4 meters per second. This is usually a story of, for example, someone's sitting on a bicycle and they're just coasting away. While they're coasting away, they're not doing any work. All right. Now, if for any reason they want to, they see a yellow light and they want to, break the law and just go right through the yellow light, that's when they're going to put the pedal onto the metal. You're doing your real work in accelerating your bicycle. While your bicycle's coasting, you're not doing any work. Okay, so that 4 meters per second is previous energy you had already in the past. We're talking about the work required to accelerate from 4 meters per second to 8 meters per second. Okay, so keeping that in the back of your mind, really, we're just solving for work. Work is equal to delta E. Okay, as I said, you already had energy at the beginning. That kinetic energy of you already in motion at 4 meters per second. You're not doing any work there. Inertia is moving you forwards. Okay, so if work is equal to the change in energy, and the change in energy in this case over here was whatever kinetic energy you had while you're at 4 meters per second, and how much kinetic energy you have at 8 meters per second, then yeah, you're just looking for the difference of those two. So 1/2 times 1 meter times 8 meters per second squared, subtract 1/2 times 1 times 4 meters per second squared. Yes, that will give you your 24 joules. Okay, if we were to go through and do that extra step, what we'll find out is that we had 8 squared is 64, divided by 2 is 32 joules. So when you're moving at 8 meters per second, the kinetic energy that you have in the bicycle is 32 joules. That is true. Remember, the first quantity you had, the bike was already in motion. So 4 squared is 16, divided by 2 is 8 joules. So that's why you had to take away the 8 joules, because you didn't work for it. You were already in motion. It's almost as if, you started from a hill and you coasted downwards, and now you're cruising at 4 meters per second, and now you want to start burning calories, all right? So that's why you had to technically subtract the 8 joules. All right, so I hope that logic there makes sense for you, okay? Now, for others, we'll be wondering, well, why is there such a huge difference in this? Well, take a look at the formula here. And here's the important thing. Is your kinetic energy directly proportionate to your speed? And if you look at the formula carefully, it's not. It's a quadratic relationship. All right. Kinetic energy and your speed is not a direct correlation. It's a quadratic correlation. You want to double your speed? Well, now you need 4 times as much energy. You want to triple your speed? Now you need 9 times as much energy. That's one of the limitations we have about traveling into deep space, all right? Now, this is not the total correct answer, but it alludes towards it, and hopefully you have a better appreciation of it. So the faster and faster you try to go to the speed of light, well, the energy that you need doesn't increase linearly, all right? So in other words, you want to travel twice as fast, you can't just use twice as much energy, you need to use significantly more. So that's one of the issues about traveling, through galaxies. You need an immense amount of energy just to get really fast. There's also this thing called the speed barrier, all right, that no object can travel faster than the speed of light. So that creates another limitation and another extension to this equation, which makes these formulas crazy long, all right? Because now that formula will be about, I think, about 3 times as big as what you're seeing there, maybe even 4 times as big. And you'll see that formula in grade 12 physics. Okay, so really, right now, we're dealing with problems that are far slower than the speed of light, and these formulas are 100% correct as long as you go slower than the speed of light. I think once students already know about it because they've seen it in the past, no, that's not it. That's just cleaning this up. All right, so what you've done over there, a student was asking, can I just do that? Well, what the student effectively did is that when they looked at this, they said, hey, there's a 1/2 in both of these terms. Why don't I factor it out? There's an m in both of these terms. Why don't I factor that out? And lastly, VF squared and VI are the 2 that we can factor out into. Okay. Now, if you want to show this formula and then show this afterwards, I'm okay with that. Okay. All right, so if you want to show that and show that afterwards, you can, and you will get to the right answer, and I'll give you full marks for it. I just don't want people to jump right to this formula officially, because that's not an official formula. That is a derived formula from your previous understanding. Okay. So yeah, you are correct, but remember that's been derived by rearranging what we just solved earlier. Any other questions, guys? One last picture for you. Why not? I didn't realize I had it animated out. I'm just drawing this out now. As I mentioned, it's a quadratic correlation. Okay, so as your speed increases, your energy does not increase linearly. It increases quadratically. In other words, the amount of energy that it took for you just to get to your 4 meters per second, yeah, that's how much energy you needed to get to there, which was, what is it, 8 joules, right? But to go up to 8 meters per second, it's not 16. It increases quite significantly, right? It jumped up all the way up to 32. And here we're looking at the difference between 32 and 18 joules, and that's how we got to our 24. So that's a visual way of seeing how we got to our 24 joules. We're looking at the difference between those two states. And work provides that path. It's not a state. Okay. So example 5, I'll just leave this for you guys just as practice on your own, and I'll just pop up the answer key afterwards. All right. And this is just an exercise of, first off, using the correct units, and number 2, knowing how to properly rearrange your equation. For homework tonight, guys, course pack page 42, questions 1 through 7. Okay. I'll pop up this part over here just so it's in the video recording, and I'll just leave that for your own personal study on how to rearrange the equation. Okay. Aside from that, I just want to stop the video,